Hello, Bill Nye here, and today we're going to unravel a fascinating story that happens every time you use your computer. Let's dive into how your computer's brain, the operating system, communicates with all its parts, orchestrating a seamless symphony of hardware and software. You interact with your computer using keyboards, mice, screens, speakers, and printers, each one a unique tool for a specific job. These are called devices, the hands, eyes, and ears of your computer, allowing it to sense and respond to the world around it. But how do these devices actually communicate with the operating system? The answer lies in something called device drivers. Our goal today is to understand this vital connection, which is often invisible but absolutely essential. We'll explore why device drivers are crucial for your computer to function properly, and how they act as translators between hardware and software. Without device drivers, your hardware wouldn't know how to work together, and many devices would simply refuse to function. Device drivers are special pieces of software that let you plug in new gadgets and have them just work. No extra effort required. Let's start with the basics. Input and output devices, or I/O devices, which are the main channels for information flow. Input devices send information into your computer, like keyboards, mice, microphones, and scanners, helping you interact and communicate. They're how you give commands and data to your computer, making it possible to control and direct its actions. Output devices take information out, like monitors, speakers, and printers, turning digital signals into sights, sounds, and printed pages. They show you results, making digital information tangible and enjoyable in your everyday life. Input and output devices are the messengers between you and your computer's digital world, bridging the gap between human and machine. Now let's see how the operating system manages all these conversations, ensuring everything works together in perfect harmony. The operating system is like a traffic conductor, managing requests from all your devices at once. It oversees input and output operations, ensuring data flows smoothly between the CPU, memory, and peripherals. The OS issues commands to devices, tracks their status, and handles interrupts, signals from devices needing attention. For example, when you click your mouse, the OS pauses, handles the click, then resumes its work. The OS also manages storage devices, keeping your files organized and accessible. When you save or open a file, the OS finds the right spot on your drive. Networking is another big job. The OS manages your network card, packages data, and ensures secure communication. It handles IP addresses and protocols, letting your computer talk to the world. The OS is the ultimate gatekeeper for all information moving in and out. How does the OS actually talk to a device? It's not magic. There's a well-defined process happening under the hood every time you interact with your computer's hardware. The operating system communicates with devices through special memory locations called registers, which are built right into the hardware. There are three main types of registers. Control registers, which the OS uses to send commands and instructions to the device. Data registers, which temporarily hold information being transferred between the OS and the device. And status registers, which the OS reads to check the current state or health of the device. For example, the OS writes a command to a control register to start a hard drive spinning up, or to initiate a read operation, or checks a status register to see if a printer is ready to receive data, or if it's still busy printing. Data registers act as temporary holding areas for information being transferred, making sure data is available when needed. Status registers tell the OS if a device is busy, ready, or has encountered an error, so the OS knows exactly what's happening at any moment. To make transfers efficient, devices often use FIFO buffers, first in, first out memory that acts like a queue, storing data in the order it arrives. The CPU can quickly dump data into the buffer without waiting for the device to catch up, and the device processes it at its own pace, pulling data from the buffer as it becomes ready. This prevents the CPU from waiting around for slow devices, allowing it to move on to other tasks and keep the system running smoothly. Registers and buffers are the key to smooth communication between hardware and software, acting as translators and traffic controllers for data. They let the OS coordinate actions with the physical state of each device, ensuring everything works together seamlessly. Now, let's look at how data actually moves from one place to another in a computer system. There are two main ways the OS moves data: Port-mapped I/O and memory-mapped I/O. Port-mapped I/O uses special addresses for device registers, separate from main memory. Memory-mapped I/O maps device registers directly into the computer's memory space, making access easier. The simplest transfer method is programmed I/O. The CPU handles every step, checking device status and moving data byte by byte. This is easy but inefficient, as the CPU is tied up the whole time. Enter Direct Memory Access, or DMA. With DMA, the CPU sets up the transfer, then a DMA controller moves data directly between device and memory. The CPU is free to do other tasks while the transfer happens. When finished, the DMA controller notifies the CPU. DMA is much more efficient for large data transfers. These methods let computers handle everything from simple keystrokes to massive file copies. Efficient data movement is crucial for performance. Next, let's see how devices differ. Devices aren't all the same, they differ in how they access and handle data. Random access devices like RAM and hard drives let you jump directly to any piece of data. Sequential devices like tape drives require you to go through data in order. Sequential devices are slow but useful for backups. Devices are also classified as character or block devices. Character devices transfer data one byte at a time, like keyboards and mice. They use a stream-based interface for unstructured data. Block devices like hard drives and SSDs transfer data in fixed-size blocks. This is efficient for storing and retrieving large files. The OS requests specific blocks, making storage fast and organized. Understanding device types helps explain how your computer manages everything from typing to saving files. Now let's talk about the software that makes it all work. Device drivers. Device drivers are the translators between the OS and hardware. Each device needs a specific driver to communicate with the OS. The OS gives a generic command, and the driver translates it into instructions the hardware understands. Without the right driver, the OS can't use the device. Drivers ensure compatibility. Manufacturers release new drivers for new devices, so the OS doesn't need to know every device in advance. This lets hardware and software evolve independently. Drivers also impact performance. A good driver unlocks advanced features and speed. A bad driver can cause crashes or slowdowns. Graphics card drivers, for example, are highly optimized for speed. Keeping drivers updated can improve your computer's performance and stability. Next, let's see how drivers get installed. Installing drivers is easier than ever thanks to plug-and-play technology, which has revolutionized how we connect devices to our computers. When you connect a device, it identifies itself to the operating system, letting the computer know exactly what kind of hardware you've plugged in. The OS checks for a built-in driver and installs it automatically. Your device works in seconds, often without you needing to do anything at all. If there's no built-in driver, you may need to download and install one from the manufacturer's website, especially for specialized or newer hardware. On Windows, Device Manager is your main tool for managing drivers. Here, you can update, roll back, or manually install drivers for any device. If a device has a problem, Device Manager flags it for you with a warning icon, making troubleshooting much easier. Modern systems handle most conflicts automatically, but older hardware or legacy devices can still have issues that require manual intervention. On Linux, most drivers are built into the kernel as modules, which are loaded as needed to support a wide range of devices. Plug in a device, and the kernel loads the right module. No manual install needed for most common hardware, making Linux surprisingly user-friendly. However, proprietary hardware may require a separate driver, which you might need to install from a CD or download online. On Linux, devices appear as special files in the dev directory, allowing the system and users to interact with hardware directly. On macOS, most drivers are built in, and Apple manages compatibility tightly, ensuring a smooth experience for most users. For third-party devices, simple installer packages make adding new hardware straightforward and user-friendly. For printers, systems like Cups manage drivers and print jobs across Linux and macOS, streamlining setup and daily use. No matter the OS, drivers are the essential link that makes your hardware work seamlessly with your computer, bridging the gap between technology and usability. Devices and drivers are the unsung heroes behind every click, sound, and image on your computer. The OS manages the flow of information, using registers, buffers, and DMA for efficiency. Device drivers bridge the gap between generic OS commands and specific hardware needs. They ensure compatibility, unlock performance, and make plug-and-play possible. Keeping drivers updated keeps your system running smoothly. If a device isn't working, check the driver first. Understanding drivers demystifies your computer and empowers you to troubleshoot. Thanks for exploring the science behind your computer with me.